Hello everyone. So now we will move on to section 2.8, and here we will study about a particular type of equation called the Eikonal equation. So this is a nonlinear equation. We will see how to solve this equation. So consider the two-dimensional Eikonal equation. Here dimension is 2 because you have x and y. So the equation is ux square plus uy square equal to n square, where n is a function of x and y. This is the equation of a Eikonal equation. Here u of xy equal to c are the wavefronts and n is the refractive index of the medium. So n can be a function of x and y. This equation has got many physical application. So it is important to solve this PDE. Now we can see that this equation 1 can be written as dot product of two vectors. We can write this as ux uy n square dot ux uy minus 1 equal to 0. Now we know that as we have studied in the theory of PDE in the first section, we have seen that ux uy minus 1 is a normal which points downward to the surface. And we have seen that this represent dx by dt, dy by dt, du by dt. So this dot product is 0, this is normal, hence this must be orthogonal to this, hence this vector must be in the tangent plane. So this must be in the tangential plane. So from this we can conclude that dx by dt should be ux, dy by dt should be uy, and du by dt should be n square, because this vector is tangent to the surface, dx by dt, dy by dt, du by dt. Now since we do not know what is u, our aim is to solve for u. So we will differentiate this once again so that we will get an equation independent of u. So when you differentiate this once again, we are getting d by dt of ux. So we will get it as, here we have d by dt of ux. So we have the product rule we have to use. Ux is a function of x and y. So we have to first differentiate ux with respect to x, then x with respect to t, plus ux with respect to y into y with respect to t. Now we know that dx by dt is ux, dy by dt is uy. Now now this can be written as derivative of ux square plus uy square, because derivative of ux square with respect to x is 2uxx. Okay, so we have 2ux is there, then uxx. So for that we have written half here, so that 2 will get cancelled. And derivative of uy square with respect to x will be 2uy, uxy. Now this can be written as, we know that ux square plus uy square is nothing but, it is n square. Here we have the equation is ux square plus uy square equal to n square. So we have equation number 2. So this represents half n square of xy, derivative here this represents derivative with respect to x. Now similarly we can do for d square y by dt square, and we will get in the same way it as half derivative of n square with respect to y. Okay, we mark it as equation number 3. Now what is du by dt? Now du by dt is total derivative of u with respect to t, which we can write it as ux dx by dt plus uy dy by dt. Now dx by dt is ux, dy by dt is uy. So from here you will get n square of xy. That is du by dt is n square of xy. Now if you integrate it from 0 to t, we will get u. What is u? So when we are integrating from 0 to 2, u of x y, x of t, y of t minus u of x of 0, y of 0, which is equal to integral 0 to t n square x of 2, y of 2 d2. Now here xy is a solution of equation 2 and 3. You can see that equation 2 and 3 are independent of u, and we can find the solution easily if we know what is n square. So we can find d square x by dt square and d square y by dt square. From this we will get the characteristic x and y. Then du by dt we will get from here. Now here we see that in equation 2 and 3 they are second order equation. Here we have d square x by dt square. So here we need to solve a second order ODE. Now when we solve this, we need at least two conditions to get the arbitrary functions here. So one, we have the if in the problem initial data is given, we will get one initial condition. Now to find the arbitrary functions completely, we need one more initial condition, and which must be the derivative, the direction of the tangent at that point, that is the derivative xt by t. So we must get at the origin, that is at the initial condition, what is xt by t, and this xt by t is nothing but ux uy. From here we have xt is dx by dt, so we have seen that dx by dt is ux, dy by dt is uy. It means that we must get ux uy at the initial data, and ux uy is nothing but gradient in the xy plane of u. This is the gradient. Now we will see how to do problems. So question number 1, that is example 2.16. Solve the equation ux square plus uy square equal to n naught square, where n naught is a constant and the initial condition is u of x comma 2x equal to 1. So here you can see that RHS of the Eikonal equation is a constant, and the initial condition is u of x comma 2x equal to 1. So the u is 1, it is a constant on the line y equal to 2x. Okay, this when y is 2x. So this the initial condition represent the line y equal to 2x. So on the line y equal to 2x, u is a constant. So here you can see first initial condition we will get from here, and to get the second initial condition we need to find del u, that is gradient of u. But since u is constant here, we will see how to find the second initial condition. So as we did in the theory part, we have dx by dt is ux, dy by dt is uy, du by dt is n naught square. Now as we did in the from the theory, we have d square x by dt square is half partial derivative of this n naught square with respect to x. But here we have n naught is a constant, so its derivative is 0. So we have d square x by dt square equal to 0. Similarly, we have d square y by dt square is 0 because n naught is a constant. Now since they are second order equations, we know how to solve this. So we get that the characteristics are straight line. X of t and y of t are nothing but they are straight lines, because if you integrate this 2 times you will get straight lines. Now so we have characteristic. How we can write the characteristic? X is f1 of s t plus f2 of s, y is f3 of s t plus f4 of s, and one of the initial condition we have that u of x comma 2x is 1. So x at 0s is s, y at 0s is 2s, u at 0s is equal to 1. So this initial condition we have. Now we need to find the second initial condition also. Now for finding the second initial condition, we have to find xt by t, which is same as ux uy, that is the gradient of u we have to find. But in this problem, u is constant on the initial line y equal to 2x. So we see that the gradient of u is orthogonal to the initial line y equal to 2x. Now how this is orthogonal, that I have explained here. How we are getting that gradient of u is orthogonal to the initial line. That explanation is here. So we have u of x comma 2x is equal to 1. I'll consider this function as a composition of two functions. Okay, so the first function f is defined as f of t comma 2t, and second function acts like this, u of t comma 2t maps to 1. So this function is a composition of two function u composition f, which is a mapping from alpha beta to r. Okay. Now since u is constant, its derivative is 0. So u composition f, its derivative is 0. Now how to differentiate this? This is nothing but u dash of f of t dot f dash of t. Now u dash of f of t, since u is a function of more than one variable, u dash represent del u, gradient of u, dot f dash of t. So del u dot f dash of t equal to 0 means what? These two are orthogonal. So gradient of u is orthogonal to f dash of t. What is f dash? F is a mapping from alpha beta to r to f is defined to be t comma 2t. So f dash is always tangential to it. Okay. So f dash is tangential to it. So it means that gradient of u is orthogonal to the line y equal to 2x. It represents y equal to 2x. So gradient of u is orthogonal to the line y equal to 2x. So I have provided explanation to this sentence. That is, gradient of u is orthogonal to y equal to 2x. Using this fact, since it is orthogonal, we have del u dot f dash of t equal to 0. Now del u is nothing but ux uy, and f dash of t, f of t is our t comma 2t. So f dash of t is 1 comma 2. So ux uy dot 1 comma 2 equal to 0. So we have ux plus 2uy equal to 0. Also we have the problem in the given equation is ux square plus uy square equal to n naught square. So we can solve these two equations and find the value of ux and uy. Okay, so what I did is I have found uy from here and substituted here. So here also you will get two values, plus or minus is there. I have taken only one part. Okay. Ux I have taken 2n naught by root 5. So substituting the value of ux, we will get uy minus n naught by root 5. So ux uy are nothing but they give the second initial condition, that is dx by dt of 0s is 2n naught by root 5 and dy by dt of 0s is minus n naught by root 5. We mark it as equation number 2. So we got two initial conditions and we have the equation of characteristics. What are the characteristics? Now we have the third one. First two we have solved. Third equation is du by dt equal to n naught square. So if you integrate this, you will get u equal to n naught square t plus f5 of 6. Now we will apply the initial conditions. We have the this is the equation of the characteristic, and we have the two initial condition. Now when we apply it, you will get, so when you apply the first condition is x at 0s is equal to s. So when t equal to 0, x is s. So you will get f2 is s. Similarly f4 you will get as 2s and f5 you will get as 1. So that value is substituted. Now the second condition is derivative dx by dt. So when you do dx by dt, here you will get f1 of s. So you will get f1 of s is equal to the first one here, that is 2 by 5. What we are getting, 2 by root 5 and naught. Okay. Similarly you will get f3 of s as minus n naught by root 5, and so that's all. So we have substituted the values here. So this is the equation of the integral surface. This is the parametric representation of the integral surface. Now again, to write the integral surface, to invert the representation, we eliminate t and s and we write u as a function of x and y. So for this you can use any method. You have to eliminate t and s and write u as a function of x and y. in this what I did is I multiplied this equation by 2 and subtracted from y. So I got the value of t as 2x minus y by root 5 n naught, and then I have substituted the value of t in u. So by simplification you will get u of xy equal to 1 plus n naught by root 5 2 into 2x minus y. So this is the required equation of the integral surface. Okay.